Students, today we are going to study alternating current AC through LCR circuit. Here you see LCR, they are connected in series. We have considered one inductor, one capacitor, one resistor. They are connected in series with a supply, with a source E. Here you see one coil with capacitor, then one resistor. Finally, these two ends are connected with C. Here you see they are connected with source, so that current I flows throughout the circuit. Since coil, capacitor and resistor, they are connected in series, so potential difference will divide accordingly. See, VL for this coil, we have written VL across the coil, VC across the capacitor, VR across the resistor. Let VL, VC and VR be the instantaneous values of voltages across L, C and R. Now, from Ohm's law, we know that V is equal to IR. So, for this coil, for inductor, we will consider VL is equal to I psi L. For this capacitor, VC is equal to I psi C, and across the resistor, VR is equal to IR. Here, psi L is equal to omega L and psi C is equal to 1 upon omega C. In order to find the relation between E, VL, VC and VR, let us draw a phasor diagram for current and voltage. See, on y-axis, we consider voltage, and on x-axis, we generally consider current. Now, see, this broad line represents, see, drawn on OX axis, OA is for current. Let VR V voltage across resistor we consider on this axis. Then on Y dash axis we have taken for this smaller distance VL minus VC, and here O to Y dash it is VC. Why? Because you see, here in case of AC through inductor, we get EMF leads current by pi by 2. In case of AC through capacitor, EMF lags behind the current by pi by 2. And for resistor, AC through resistor, we get current and resistance, current and voltage on the same phase. Here pi by 2, phase difference is pi by 2, again pi by 2. Here EMF leads the current by pi by 2. In case of capacitor, EMF lags behind the current by pi by 2, and here in case of resistor, they are in phase. Now, in, in order to find the relation between E, VL, VC and VR, let us draw a phasor diagram. It is called as phasor diagram. Let us draw the phasor diagram of current and voltage. The phasor diagram, in the phasor diagram, you see current is considered on x-axis, whereas voltage on y-axis. Now see, some broad lines are here. It is for particular VR, VC and VL. Now I am explaining the phasor diagram. See, let OA, OB and OC represent the magnitude of VR, magnitude of VL and magnitude of VC respectively. Since VL more than VC, the line here see OD, this line OD shows VL minus VC, the resultant of VL and VC. OE is resultant of OA and OD. See, in triangle OAE, now we consider this triangle OAE. Now before going to this triangle, here you see E makes an angle of phi with OA, and with this OA we are having VL minus VC on y-axis, and it is making an angle of pi by 2. Now see, VC is here, you see OC represents VC, and here I am repeating once again. You see OA represents VR, OB represents VL, OC represents VC. Since VL is greater than VC, so OD shows VL minus VC. Here you see I have drawn one dotted line, so that you see we are having one right angle triangle. Okay. This OE makes an angle of phi with x-axis, and VL minus VC makes an angle of pi by 2. Again, VC makes an angle of pi by 2. Okay. Now you see, considering this right angle triangle and using Pythagoras theorem, we can write OE is equal to square root of OA square plus AE square. Since this AE is equal to OD, so for this AE we can write VL minus VC. Substituting the values, we get E is equal to square root of VR square plus VL minus VC whole square. Now we know that we are having some values for VL and VC. VL is I xi L and VC is I xi C, and VR is equal to IR. All these are from Ohm's law. Substituting the values, we can write E is equal to IR square plus I xi L minus I xi C whole square. Now, we can take I common. So, next step, we can write E is equal to I into square root of R square plus xi L minus xi C whole square. From this relation, we can write I is equal to E divided by square root of R square plus xi L minus xi C whole square. Now, in case of LCR series circuit, we have got I is equal to E upon square root of R square plus xi L minus xi C whole square. Let it be equation number 1. The effective opposition offered by L, C and R to alternating current is called impedance of the circuit. Impedance of the circuit. Impedance of LCR circuit. And impedance is represented by Z. So, using this relation, considering equation number 1, we can write I is equal to E upon Z. Let it be equation number 2. Now, from equation 1 and equation 2, we can write Z is equal to square root of R square plus xi L minus xi C whole square. Now, if we substitute the value of xi L and xi C, we can write Z is equal to square root of R square plus omega L minus 1 upon omega C whole square. Let it be equation number 3. Let it be equation number 3. Now, from phasor diagram, again consider phasor diagram. E leads current by an angle of phi. Okay. Again we consider right angle triangle OAE. We can write tan phi is equal to AE perpendicular upon OA. OA is base. Tan phi is equal to AE upon OA. Since these two are equal, so for AE we can write VL minus VC. Substituting the values, we get tan phi is equal to VL minus VC upon VR. Substituting the values, we can write for VL I xi L, VC I xi C, for VR I R. Since I is common, we can take out, and after cancellation of I, we can write tan phi is equal to xi L minus xi C upon R. Now, substituting the values for xi L and xi C, we can write tan phi is equal to omega L minus 1 upon omega C divided by R. Let it be, this one is very important relation. Let it be equation number 4. Equation 4 gives the phase angle phi by which AC alternating for this particular circuit. We are talking about LCR series circuit. Equation 4 gives the phase angle phi by which AC EMF leads the current for particular condition, that is xi L greater than xi C in an LCR series circuit. Since Z is equal to square root of R square plus omega L minus 1 upon omega C whole square. This Z is the effective resistance of series LCR circuit, which opposes or impedes the flow of current through it. That's why it acts as a resistor. So SI unit of impedance Z is same as resistance, that is ohm. The relation between R, xi L, xi C and Z is shown by the triangle. See, one right angle triangle we are having, triangle OAP, where OA, for OA, C, R is here on OA, AP, xi L minus xi C and OP is Z. This right angle triangle OAP is called impedance triangle. The right angle triangle OAP is called impedance triangle. Here we are having some special cases. Number 1, when xi L is more than xi C, in that case we have tan phi is equal to xi L minus xi C upon R, or from this right angle triangle you see cos phi will be R upon Z. In that case, the series LCR is said to be inductive. When, second case, when xi L is smaller than xi C, in that case tan phi is equal to xi C minus xi L upon R, or cos phi will be R upon Z. The series LCR is said to be capacitive. Third case, when xi L is equal to xi C. Substituting xi L is equal to xi C for tan phi, we get angle phi is equal to 0. The series LCR is said to be resistive.